We will start, and like Ranjit mentioned, please, as you are, help us to keep this under control with muting your phone and the camera so we can have the maximum benefit of the available bandwidth and the quality. Today we will have, I would say, an introduction to bearing damage analysis, and we will use the ISO classification. Please help us to mute the phones, mute the microphones. We will, as I was saying, have an introduction because we only have 45 minutes, and this is a topic that we could speak for much longer. Usually our training on the subject will last 2 or 3 days, depending on the, let's say, starting point. So this is important because I want you to see that we will have a short overview of the main failure modes and what do we need to know or understand about the bearings to have a better interpretation of the symptoms and the features and the characteristics that we see on the bearing components themselves. As we go through, I will ask you to write your questions on the chat so we can try to answer them by the end of the session today. When you look at bearing failures, I know this may sound a bit funny, but it's not a funny situation when you are facing failures on critical machines. And this is basically one of the many statistics that you can see around in bearing failures. The numbers, please help to mute your microphone. Let's see if we can keep everyone on mute, please, to make sure that the communication is clear. What I was saying is that the numbers in terms of percentage of different type of failures will change from one situation or one company or one industry, and even within the same industry from one side to another. So the numbers are not that relevant, but we can say that many bearings do not reach their expected life because of reasons other than the bearing manufacturing or its characteristics, whether they can be related to lubrication or contamination or installation and many other things. So there is a lot we can do to try to improve and try to solve some of these issues if we understand, when we look at the bearing, what is the most likely reason for the failure. But one of the things that I wanted to be very clear today, because we have such a limited time, we are not going to be able to cover this, let's say, deeply and thoroughly as we would like to. But I would say 2 takeaways that you can take from today's session is that if it is too late, it's too late. And many times when we get our bearings for analysis or investigation, the bearing is in such a terrible condition that it's practically impossible to know how the failure started. And what we need to be aware is that one initial failure will lead to a lot of consequential damage if you allow the bearing to continue to run. And we all know that many times production pressure will not allow us to stop the machine early enough when we, let's say, detect the first indications of a failure. But the more we continue to run the bearing, the less likely is that we are going to be able to really understand what happened, what was the initial trigger. So that's one of the takeaways. The second one is do not forget that the bearing is part of a system. So the picture that you see on the left is a cut section that shows the material, and you can do a metallographic analysis. And I've seen many times, and we see in SKF many times, that we tend to focus on the details, on the very minor details. So that's why the title, Look at the Forest. You need to understand the bearing as part of a system, and many times indications or confirmations of the possible failure hypothesis you can find on the components around. You need to look at the shaft, you need to look at the housing, you need to look at the seals, you need to look at the bearing as part of a system. And even when you're looking at one bearing failure on, let's say, a motor, a gearbox, or something like that, the bearing is sitting on that shaft together with another bearing, most likely. And you need to look at what happened with the other, when I'm talking about the other components, is also the other bearing and even the other bearings if there are more, because they might also give you some clues about what might have happened. And one of the, let's say, critical points to understand bearing failures is that you need to understand the bearing in itself, so you know what to look for. This sounds very basic, of course, and you can say we can identify the bearing components and the different surfaces and the different features. But this is a critical basic knowledge for you to understand. When you are looking at the bearing, you know what you are supposed to see and what might be considered as normal, because when the bearing starts running, there will always be some kind of contact pattern between the running elements, whether balls or rollers, and the raceways, between the running elements and the cage, and between the rings and its supporting surfaces, the shaft or the housing. So we need to have an idea of what is a normal contact pattern in which position, so we can then look at the bearing and see if what we are, let's say, inspecting and evaluating makes sense in relation to what is the bearing design. And of course, different bearings have different number of components, so that's why it's not enough to have a very general understanding, but sometimes even different manufacturers may have different design features. So even if the bearings look similar from the outside, they might have different internal features. So you need to understand these differences to know what to look for, and again, what is a normal contact pattern from what is not. This is an example of those features. You can have many different cage types, and even within the same bearing, it might have different cage executions. What I mean is, they can have pressed steel cages, they can have solid brass cages, what we call machine cages, or you can have molded cages from polyamide and other synthetic materials. So that's one of the characteristics that you need to understand. But like I said, within the same bearing, you can have different variants, and then those variants may involve, for example, what is a cage execution. So even, I would say it's not enough to know that the bearing has a brass cage, but that brass cage in the same bearing can have different executions. For example, it can be guided so you can see the cage weight supported by the running elements. So there should be no contact between the cage and the rings. So that would be a small, let's say, consideration when you actually see the cage and you see if there was contact with the, let's say, surfaces on the rings, then there is an indication of a problem. The same bearing can have an inner ring guided cage, and when we say inner ring guided cage, what we are talking about is that the weight of the cage is supported by the inner ring. So there is, of course, some gap, and that is not shown on the picture, but the weight of the cage goes around on the inner ring, or it can be guided on the outer ring. So those are features that are important to understand. Again, what is supposed to be there, what is a normal contact pattern, and what is not. Another consideration, and these are just a few examples of understanding your bearing and understanding your application when you are looking at characteristics and features on a failed bearing. In most applications, you will find a locating and a non-locating position. So this is also connected to what I said before, that you need to look at the bearing as part of a system. So let's say that you have a bearing that failed, and you think that one of the possible reasons for the failure is axial load being applied to the bearing. And then you wonder, if you look at the bearing in isolation, you need to answer, and might not be able to answer, whether that was the bearing in the locating or the non-locating position, because it might be completely different interpretation. If you have indication of an axial loading on the bearing that is supposed to be non-locating, then that's an indication that there is something wrong, because that bearing it is not supposed to take any axial load. So again, it's important to understand the bearing in the context of the application to look for what is, I'm sorry for repeating, what is normal, what is supposed to be there, and what is not supposed to be there. So let's, I mean, these are just some very basics, and I cannot go into more details because of the limited time. But let's look at some of the load patterns. I was mentioning before that even under normal conditions, the bearing will develop some contact pattern under normal load, normal lubrication, in a normal environment. You can say a typical bearing application might look like a rotating inner ring with a stationary outer ring, which means that with the remaining clearance inside the bearing, the inner ring, as the ring is moving around. Do you see that? As soon as I put my... let's see if we can mute. Yeah, thank you. So the inner ring, as the inner ring is moving around, will develop a contact pattern that covers 360 degrees, right? So you will look at the inner ring, you will look at the raceway, and you will see that there is a clear contact pattern that should be there if this is the operating condition, a constant low direction, inner ring rotating, so the outer ring will only experience the load as the running elements are going through the what we can call the loaded zone. It might be typically, in a normal situation, somewhere between 120, 150 degrees. So if you are looking at an application like this, and then you see something different, that is already an indication that there might be something wrong, because you don't see what you are expecting to see. And of course, the rolling elements are shown here also with color, because they all go around the load area. So that's the idea, that as the bearing components go through the load area, or the load direction, the area of the bearing which will experience the load, they will develop some kind of contact pattern. And I will show just one example because of the limited time. So in this case, for that, let's say, preceding condition, the rotating inner ring, a constant load direction, you will see that the contact pattern on the inner ring raceway of this ball bearing will cover 360 degrees. It will be centered because there is only radial load. In this case, there is no axial load being applied. So the contact should normally be in the center. And if it is not, that might be an indication that something is not as expected. And the outer ring, which is not rotating, should only have a contact pattern in the load area, which is not of a constant width, because it will be, let's say, wider in the area of maximum load and smaller or thinner as you move in or out of the loaded zone. So that is what is expected to be normal in an inner ring rotation with a constant load direction and a constant load. This is a very simple example of such a condition. I mean, the wheel of a crane, for example, that is supported on external bearings. So the inner ring is rotating with the shaft and the wheel, of course, and then the weight is acting as the dominant force. And the outer ring, then in this case of these two bearings, the locating on the right, the non-locating on the left, the outer rings will experience load only on this area of 120 to 150 degrees. So that's that is just one example of one application where you will see something like that. And then you can make this kind of logic to any of your machines. Of course, it means that you need to understand what loading type, what loading conditions. It is a constant direction, it is changing direction, it is a rotating load like in a vibrating screen. So you need to have that understanding to then connect that with the load pattern that you see on the bearing. And of course, there are many other possible situations and combinations like outer ring rotation. If you have outer ring rotation and a stationary inner ring, then of course the logic will change. You will see a contact pattern on the outer ring all around and only on one part of the inner ring. You can have a bearing that is supporting axial load and not radial load, like sometimes happens on a vertical shaft. But it can also be that there is a dominant axial load on a horizontal shaft, and then the bearing that is supporting that axial load will experience a contact pattern all around on both rings. You can have combined loads, more radial load, more axial load, and that will change the contact pattern on the inner rings and the outer rings, also depending on which one is rotating and which one is stationary. So this is basic, it's common sense, but we need to have these considerations to connect what we see on the bearing with the application. And of course, I highlighted in red here also contact patterns that apply to situations that are indications of a failure already. For example, when you have the outer ring of a bearing misaligned with the inner ring of the bearing. So in those situations, you have an indication already in the contact pattern that there is a problem. And of course, when I'm talking about misaligned rings here, it does not mean misalignment between the driven and the drive shaft. This is the misalignment can happen within the bearing itself because of let's say, a lack of concentricity and coplanarity within the bearing itself, for example, between the shaft seat and the housing seat. You can have out-of-shape supports. The example on the picture here, it's an ovalized housing. It can happen that the housing has worn out and then somebody has been using small shims to supplement the gap, and then the complete support is deformed, and you have like an oval housing. So that will develop a specific contact pattern that is an indication of a failure already. Or you can have also excessive interference. You know, the shaft is far too big, or the housing is far too small, and then the bearing is running out of clearance, and that will develop another contact pattern that is an indication of a possible failure. So again, these are just a few examples of the contact pattern that may be an indication of a normal or abnormal situation if you make the correlation with the application and the operating conditions, of course. So let's look a bit onto this ISO 15243. The last edition is from 2017. And this is this failure classification was developed as it happens with many other ISO committees by participants of the bearing industry. So basically ourselves, SKF and other bearing manufacturers have representatives in this committee. And then there was a need basically to develop a common language because you as customers were having different interpretations and different naming conventions for the same failures. So the main idea of this ISO classification was to say there are a number of failures that can be, let's say, identified with simple tools by visual inspection without detailed material investigations or laboratory analysis. That we need to agree on how to call them. So when somebody is making an investigation and is referring to a failure, others can understand what we are identifying. So that was the main reason for this ISO failure classification, but by no means this covers everything. This should be always in the back of our mind when we are doing bearing investigations, that these are, let's say, the typical failures that can be identified by visual inspection or with simple tools, but there may be many other failures that are not covered in the ISO classification. So we will see some examples of these different failure types. And what we did here was to help to identify, because sometimes we show a picture of a ring or only a part of a ring. So we put the image on the bearing type to make sure that we understand which bearing are we talking about for the different failure types. And I have to say that this is something that is built on experience. It's something that you need to understand the bearing, you need to understand a bit of the theory behind the bearings, but it's a lot about experience and visual recognition. So when you see something, you understand what was the, then it will be easier to see the same thing, obviously. So the first type is initiated fatigue, which is the basis of the bearing life. I mean, when you look at how bearings are selected, they are selected based on a certain load and speed combination. And the reasoning behind that bearing selection is the life calculation. And the life calculation is based on this subsurface initiated fatigue. So you can say that if a bearing has failed because of the because it reached the end of its life, it might look at the very beginning a bearing that has been running well lubricated in a clean environment with the right loading at the, let's say, appropriate speed, which is in relation to the size of a bearing and the type of bearing. It might develop a spalling, you know, the first indication, and then if you stop it right there, you might see the evidence that there is like this kind of single spall in a small area. If you let the bearing run, this will grow and it will extend, and then it will be much harder to know if this started because of a normal subsurface initiated fatigue or maybe by other means, because again, one failure leads to another, and then it might, let's say, mask or hide the origin of the original failure. So again, it's very important to capture this at a very early stage. And of course, when you talk about subsurface initiated fatigue, is not always necessarily indication, oh, that's normal. That is what is supposed to happen on the bearing. Because if you are overloading or you, for example, install your bearing, in this case is the outer ring of a self-aligning ball bearing that we show here. In this case, the housing was deformed and it was kind of oval. So there were two areas at 180 degrees apart that you see the reflected image on the mirror of this side of the ring. So you see that there are two areas 180 degrees apart where there is damage. So there is an ovalized housing. And then you can say that created more stress on the bearing, more internal loading. It's not the loading from your machine, it's the loading created because of this particular condition, and that increases stress on the material and then accelerates the subsurface fatigue. Because at the end of the day, the subsurface fatigue is a consequence of the stress level and the number of cycles. So you could accelerate what is expected to be the normal life of the bearing, which end up to be short. So that can also happen. Then we have, for example, another failure type, according to the ISO classification, is the surface-initiated fatigue, which is also called micro-pitting, or it's also called micro-spalling. So there are different names in, let's say, different countries. In America, they call it one way. In Europe, they call it another. But basically, what you see here is that instead of the damage starting, like in the previous example, below the surface, these small cracks start at the surface level. And this is usually an indication of a poor lubrication film. We have far too much metal-to-metal contact between the running elements and the raceways. And then there are small cracks being developed. And what you see on the right side of the picture is basically this microspalling, small particles of metal that are coming off. Again, if you let the bearing run, there will be more severe failure develop, more wear also develop because of the particles are creating contamination, and then it will be difficult to confirm if the initial problem was surface-initiated fatigue or something else. By the way, the bearing that we are looking at, that we show here in the middle, is a spherical roller bearing. So this is the inner ring of this bearing. This is another example of abrasive wear in this case, not surface-initiated fatigue. This is another failure mode according to the ISO classification, and this is called abrasive wear. It's also the inner ring of this spherical roller bearing taken from the side, and then you basically see here that, that there is a lot of material. If you see the shape here, this should be completely symmetrical because this is the same ring. So you see one area at 180 degrees of the other that look completely different. So this means that there was a huge amount of material that has been removed by this wear process. And usually this is associated to external contamination with small abrasive particles. And then they transform your lubricant into like an abrasive paste, like a polishing paste, and it's in a way, if you allow me the expression, eating away your bearing. If you see this on the inner ring, of course, your rollers are also worn out, your cage is also worn out, the outer ring will also have a significant wear. Again, look at the bearing, understand the bearing features, and understand the bearing operating conditions, and look for confirmation, because what you will do normally is to develop a certain hypothesis, but you need to look for confirmation. So in this case, confirmation might come from the lubricant analysis, which will be contaminated with the material coming from the bearing itself, no doubt, but there will be also evidence of external contamination in the lubricant around, maybe not the one that was inside the bearing itself. Abrasive wear, if you look at this angular contact ball bearing, this is of course the cage only and some of the balls of this bearing with a brass cage, and you see that the cage has been split in two when it should be one piece. So when you have this type of failure mode, there is no doubt that in many cases, the element that will fail first is the cage, which is the most, let's say, the softer material, the weaker element in the bearing. So if you have a worn out cage, you have a very high probability that you have a contaminated environment, and that's one of the consequences. Again, you will see a wear pattern on your rolling elements and raceways, but they are much harder, so they will take longer to develop a wear pattern. And there is another, within the same ISO classification, the abrasive wear, there is something that we would call more polishing wear on this. Again, this is the inner ring of spherical roller bearing. And you see these very shiny mirror-like surfaces. In this case, also with a lot of bands. So you see a lot of circumferential bands in different positions along the raceways. And as you see on the image, we have two rows of rollers. So both are showing this mixture of very shiny surfaces with some other circular bands, maybe brown, maybe a bit darker. What you need, I mean, this is also related to an initial stage of lubrication collapse, and there is too much metal-to-metal contact. So in this case, you can say we will probably end up later in a situation of surface distress or this surface-initiated fatigue. But in this particular case, an initial stage is that the surfaces get polished by themselves. So there is some lubricant, but it's too thin and it's not able to protect the surfaces. So what you also need to consider here when you think about these circular bands are that the rollers are not only in contact with this raceway, but are in contact with the cage and with the outer ring. So there is a transfer of different contact patterns between the different components inside the bearing. So sometimes what you see, it's a mixture of these different interactions within the bearing. There is another classification of this ISO standard, which is called adhesive wear. And in this case, what we see on the image is it's just the part of the outer ring of another spherical roller bearing. And what we see here, of course, is difficult to see at this scale in the picture, but there is a very rough surface that starts, and when you look at the bearing and you know what was the position of this ring on your machine, you can see that this is the area where the rollers are starting to get loaded. So that's also an important indication that when you look at the bearing and you want to understand what is happening, you need to identify the position, the load area. So that means, and we mentioned this in our previous session on bearing failures, that you need to identify the position of your ring or your machine, the position of the inner ring on the shaft, the position of the outer ring on the housing. So then you can make a correlation if, let's say, the load is acting downwards and this area was at a certain angle, let's say around 60 degrees from the vertical position, then you can say, okay, it makes a lot of sense that this is at the start of the load area. And the failure itself happens because of a quick acceleration. So this adhesive wear is that the rollers were not rolling at the right speed given by the inner ring, and then when they go around the load area, they have to accelerate, and it's like it happens if you, let's say, accelerate very fast your car, and then the wheel is spinning on the tarmac. So there is a transfer of material between the roller and the raceway that leaves this very rough surface. So basically what you see here is kind of a micro welding process taking place between the rollers and the raceway. This wear can also happen on, and I would say is even more common than between the raceway and the rollers. It's more common on bearings that have flanges. For example, the bearings that you see here, the taper roller bearings or the cylindrical roller bearings that have flanges, which are needed to guide the rollers. But if these surfaces are not very well lubricated, they will suffer from this adhesive wear process. So you see the picture in the middle, which is the side face of a roller on a taper roller bearing, or this one, which is from cylindrical roller bearing, and this is the companion or the counter surface on the flange. We develop this transfer of material between the roller and the flange. So again, sorry. The idea is that lubrication is extremely critical to avoid this type of situation. Another classification within the ISO is the moisture corrosion. Moisture corrosion, as obviously you can understand, in this inner ring of a spherical roller bearing is a consequence of your lubricant contaminated by water or some other corrosive media. And one of the things that you can distinguish on this inner ring raceway is that there is a certain pattern of distance between some of these marks. So this is a clear indication that there was moisture corrosion developed when the bearing was not running. So during a machine standstill period, or even if the bearing has been stored in a warehouse under very poor conditions with a lot of temperature fluctuations and therefore condensation. So you can see this even before the bearing starts running. Another example of inner rings with inner rings and outer rings here, in this case, inner ring on the left, outer ring on the right, of moisture corrosion during a standstill. Can moisture corrosion develop also when the bearing is running? Of course, but it will be more randomly distributed because there is, let's say, not enough time for the water to deposit on the running surfaces, but more on the stationary surfaces for the corrosion to take place. And of course, you can say that, for example, from the picture on the right, there were different stages, and this is one pattern that maybe is matching with this one, and this one is matching with this one. So you can say that there were different stages at which the machine maybe was not running, and the water content on the grease or oil had enough time to develop this corrosion pattern. Another classification is on this fretting corrosion, which is a phenomena that happens on loaded surfaces that have micro movements. So in this case is the outer ring of a spherical roller bearing. Again, this is a very common bearing in heavy industries like in mining and many others. So that's why we have many examples of this bearing. This bearing type, and here what you see is this reddish, shiny looking corrosion, which happens because of micro movements and the load. So basically, when you see fretting corrosion, you know that this surface was exposed to load, and there were gaps, and the gaps were, let's say, helping to develop these micro movements that release or create a wear. Small particles are coming off from the surface because of this micro motion, and they basically corrode because of the presence of oxygen. And this is growing. I mean, this is a self-feeding phenomena that it will only grow. And it's usually happening when you do, let's say, quick repairs. You replace a bearing on an existing machine, and then you find some scratches or some corrosion like this, and then it's polished away, and then we put our new bearing. And then the surfaces start to look a bit more wavy, and it's typical reason why you will see this fretting corrosion. It's not the only one, but it's one of the typical conditions leading to this. And this, what would be the consequence of this? Well, the stress, because the contact is not so good between the ring and the supporting surface, then the stress will increase, and that will add to the load and internal stress on the material, which can accelerate the failure of the bearing. But it can also, for example, mean that your coefficient of friction is increasing dramatically, and then the bearing that is supposed to be acting as non-locating when there is a heavy fretting corrosion phenomena, that bearing is not moving anymore. And then you might create, when the shaft is developing normal operating temperature, it's trying to push your non-locating bearing, and it doesn't move, and then you create an internal stress in the system that is not supposed to be there. More examples of fretting corrosion, starting exactly in the load zone. Another failure type here is called forced brinelling. This is the outer ring. What you see on the picture on the left is the outer ring of self-aligning ball bearing. Maybe less common, maybe not that familiar bearing type, but this is, let's say, a very striking example of how much damage can develop with this false brinelling, which is basically when the bearing, in this case, was exposed to vibrations and movement between the different parts, the shaft and the supporting structure, and the load, and then it's creating this wear. And because the contact of the bolts in this type of bearings on the outer ring is so small, it created a nest, basically, in the bearing. So we have other examples like this outer ring of a cylindrical roller bearing type N, where you have also this false brinelling pattern. For example, here we can see that there are some of them that are a bit deeper, which if you position the rollers, you will see that there is the roller distance on the cage. So this clearly indicates that there was some vibration when the machine was not running, but also when was running, which is probably why we have so many smaller marks. And they look, very particular characteristic is the reddish and shiny, let's say, tone or look on the surfaces. If you look at the depression with some magnification, you will notice this shiny and combination of shiny and reddish finish. Another failure type, excessive voltage, an electric current going through your bearing. In this case, we see the outer ring of a ball bearing with the damage on the ball and the ring. And this was probably happening for a very short time. As the bearing was running, there was electric current flowing through the bearing. So there may be many different situations. This might be more likely to happen when you have electrical discharge because of some welding operation. But you can also have, we have seen an increase in number of bearings with electric current flowing through the bearing on electrical motors that use variable frequency drives. So which is why some solutions have been developed, like insulating coatings on the bearing rings to break that current flow. The pattern will look different. It will look more like what we show here, when there is a continuous flow of electric current through the bearing. and it may develop in this, again, ball bearing example, the outer ring of a ball bearing develop this more washboard pattern. The images that we show together here, for example, in the upper right or the lower left, are, of course, microscopic amplifications. This image on the upper right is probably a magnification of 1,000 times. So sometimes they can be so small that they are very difficult to distinguish from surface distress or some other failure types. So in some cases, you do need to go deeper to be able to confirm what is a failure mode. So not always, let's say on the lower right, obviously we will have no doubts that this is electric current, but in some of the cases it might be very mild and very difficult to differentiate from other failures. One more here is overloading. Overloading might be, for example, when you are mounting the bearing and you are transferring the force to mount the bearing on the shaft through the outer ring and the rolling elements, the bolts on the bearing. You create dents, and then on those dents, the fatigue, like I mentioned before, the fatigue will develop faster because you have more stress on those points. Contamination is one of the worst enemies, and if you remember that funny picture at the beginning, one of the most common reasons, statistically speaking, for bearing failures is from external contamination. And you see here the example of the inner ring of a tapered roller bearing, so this one here, and a lot of plastic deformations on the raceway because of hard particles. But be aware that contamination is a very wide range of conditions. You can have soft particles and hard particles. They can be bigger, they can be smaller. The geometry of the particles, the hardness of the particles, everything will play a role on how the bearing will react. You remember that we discussed abrasive wear, and I was also talking about contamination, but in that case, probably most likely very small and large number of particles that turn your lubricant into an abrasive paste. And here we see maybe less amount of particles, maybe bigger, and then they create these indentations where stress will increase and they will develop eventually fatigue. Other example, indentations from handling. When you are mounting your bearing, this is a typical example of a cylindrical roller bearing inner ring. And when you, in an electrical motor, in let's say medium to large size electric motors, when you are trying to assemble the outer ring with the rollers that are mounted on its housing or the motor cover, and you are trying to assemble that onto the inner ring that is already mounted on the rotor shaft. And then even the slightest misalignment within this very narrow clearance the bearing has can generate this kind of dents on the raceway, which will certainly lead to rejection when the motor is tested because it will be noisy. It will develop this failure frequency pattern on your spectrums. And if you let the bearing run, then it will develop a failure on those spots. One of the last examples here are force fractures. This is again inner ring of a spherical roller bearing, and in this case, what you see is that the bearing has not any evidence of being running because it basically was exceeding its tensile stress limit, and then it failed with this fracture. So this could be a case where the bearing was mounted on an oversized shaft. Sometimes it can happen on bearings that have a taper bore, and then you are driving up the inner ring on the shaft far too much, or the shaft or the sleeve, depending on the setup. But it can also happen in some cases. We have seen that bearings are mounted on oversized cylindrical shaft by heating, and then when the bearing is cooling down, it might exceed the hoop stress limit for the material and fail at the slightest impact. This is I'm sorry. This is an example of an inner ring. You are seeing the inner ring from, let's say, the top view of a taper roller bearing. And in this case, what we had was a bearing that failed, but there was a fracture. So this is not something that we cut, but the bearing had a fracture on the inner ring. And this is an example that fractures are most of the time a consequence of something else. So when you look at the bearing, you need to be careful that you try to, let's say, blame the fracture for the failure, when in fact the fracture is a consequence of something else. So in this example, in the previous example, the fracture was a consequence of the oversized shaft. In this case, it's a consequence of fatigue. So we saw the inner ring, we saw this area of damage, and then we started looking a bit more careful that on the side of a fracture, when you see the side face, you see that there is an area of interest. There is some pattern here that is not visible from the top. So there was an additional fracture. So we remove one part of the ring here, like this. So there was an additional fracture here. Then we use that to our advantage to remove that part. And then this is what we saw. So basically, you see these beach-like marks that are a clear indication that the crack started from the fatigue, and it's typical that is starting to grow in horizontal fashion below the surface, and then at some point it starts to go in the material and then finally develop into a full fracture. So basically a fracture initiated from a fatigue or spalling area. Thermal cracking. This is again the inner ring of a spherical roller bearing, and what we are looking at is the side face, and we see that there is a kind of welding similar to the smearing that we mentioned before, but in this case on not on the raceway, but on the side face. So there was something that was rubbing under load against the side face, and that can also develop cracks. You see some of those here on the picture, and they can develop into a fracture later. So these are called thermal cracking. So these are, again, some examples very quick on typical failures for bearings. But I cannot insist enough in looking at the bearing as a system. And part of that system is also the lubricant. So analyzing the lubricant, having samples of the new lubricant, the used lubricant, doing a testing of the lubricant might also help to understand what has happened and what has been the reason or confirm eventual hypothesis of your failure. Last point here is that there is material. We are going to be sending you, we have a brochure catalog type of publication that is talking about this in greater detail. So that would be a very good reference, and this can be downloaded from our webpage. So we can send you a link to that for your reference, of course. You can also buy the international standard, the ISO 15243. Our publication is very much a one-to-one relationship to it. But you need to buy this. You need to buy this from the ISO webpage, and there is more material. Absolutely, you can search the web and you can find a lot of other publications about bearing failures and Hertzian contact failures, like this atlas that was written by a former SKF colleague many years ago. A very good publication. So. This is information you can, let's say, use on your investigations. And last but not least, I would say, don't wait too much, because when you let the bearing run so far, then it's almost, you know, you need a crystal ball to really understand what the failure was. We see it very frequently, and many times we have to apologize and say, if you, and my message to you guys is, if you have a bearing under this condition and somebody's telling you, oh, this is the problem, I would say don't trust too much, because it's almost impossible, because you don't have all the records of every parameter during operation to know exactly what changed, why change, and it's almost impossible to know what was the origin of the failure because of all the consequential damage. And also one more comment. When you look at the ISO criteria is talking about visible change of appearance. So be careful not to try to force what you see on the bearing to match the categories of the ISO. That's not the objective. If it is a clear relationship, okay, but if you don't find the connection, that's also fine. You need to investigate more to understand your failure. So the ISO is just a guideline for the most obvious cases, but it doesn't explain everything. So I think if I can say something, how do you become good on bearing failure analysis? First, you need to, this is something that you learn when you do it. There is no question. You can have the bibliography, but you actually need to see the bearings. Second, you probably need practice. And third, practice. There is no other way, guys. And I think we can go to the questions now. I hope I have, well, I have not left too many minutes, but I can extend, no problem on my side. If you have questions, we can go to the chat and see the questions there.